Hello, my name is Lubomir and I will talk about the generic image library, an image processing library I have created together with my colleague Hailin Jin. Here is a plan for the presentation. First we'll define the problem we're solving, then we'll go through a simple GIO tutorial, talk a bit about the GIO as extension mechanism, and finish up with the future plans we have for GIO. The problem statement is that images are fundamental for any image processing, graphics or video project, and yet they can be represented in so many different ways that it's really challenging to write imaging code that is both generic and efficient. Let me show you what I mean. Here is an example of a 4x3 image in which the second pixel is highlighted. Think of an image as a 2D array of pixels. A pixel defines the color at a given point in the image. The color is defined with a set of channels, in this case the red, the green and the blue channel. The same image can be represented in planar form by grouping all the red, all the green and all the blue channels together. The planar versus interleaved representation is one difference. Images may also differ in color space. They may differ in the bit depth of their channels, in the ordering of the channels in memory. Sometimes the rows of the image may be word aligned or 16-byte aligned, in which case there may be optional padding at the end of each row. These are just some examples of variations between images. Today, typically people end up writing different variations of each algorithm for every variation in image representation. The end result is lots of code that is very hard to maintain. GIO's goal is to abstract away the image representation and allow for writing algorithms once and having it work for any image type without sacrificing performance. Next we will go over a mini tutorial of GIO. In this tutorial, we will write a GIO algorithm to compute the gradient of an image. We will start very simple and gradually make our code faster and more generic. Let us for now focus on the horizontal gradient only, and let us assume that we have an 8-bit grayscale image. Also, let's use the simplest possible approximation to a gradient. In other words, the central difference. And we do that by taking the difference of the two neighbors, dividing it by 2, and storing the result into the destination pixel. Then we move to the next pixel. Let us also ignore the boundary cases. The goal here is not to write a good gradient algorithm, but to show you how to use GIO. In the next section, we will show you how to interface GIO with the outside world, and we will discuss some basic ways of navigating through the pixels of an image. Typically, images are represented with the width, the height, pointers to the pixels of the image, and the number of bytes in each row. The first thing we can do is take all of this information and wrap it into what we call GIO image view. An image view is a lightweight construct that provides uniform access to the pixels of an image. It is very small, very fast to construct, and does not copy the pixels. We do the same for the destination, and finally we call the gradient algorithm with the two image views. In this example, gray stands for grayscale, 8 stands for 8-bit channel or unsigned char, 8S stands for 8-bit signed char, C stands for constant or read-only, and view stands for an image view. GIO provides type defs for some of the most common types. First is the type and ordering of the channels. followed by the channel depth, followed by the type of channel. By default it is unsigned integral, F stands for floating pointer, and S stands for signed integral. By default the construct is mutable, C stands for immutable or read-only. Planar stands for planar organization. Step stands for constructs that have non-unit step between adjacent pixels. And view stands for image view as opposed to a pixel value, a pixel iterator, an image, etc. If we ignore performance and focus on simplicity, we can write the image gradient code as shown here. We simply loop over the pixels and write the formula for each pixel. This only works for grayscale images whose pixels are convertible to channels. This code is slow because we compute the location of each pixel based on its two-dimensional coordinates, which involves multiplication and addition. A more conventional way is to remember the beginning of each row and have a one-dimensional offset from it. Here is the code that does that. The outer loop is the same. We then initialize the iterators at the beginning of each row, and then we access the pixels as offsets from the iterators. This is called a pixel iterator. It's an STL random access iterator. If you don't know what an iterator is, think of it as a pointer. In fact, in this example, the iterator is a row C pointer and the indexing operator is a row C pointer indexing operator. GIL chooses the simplest constructs that can do the job. Now let us talk about computing the gradient in a vertical direction. One naive way to do that is to do the same but vertically. We can remember the beginning of each column and do a one-dimensional offset from it vertically. Here is again the code to compute the horizontal gradient, and here is the code to compute the vertical gradient. All we needed to do is change x with y, width with height, and row with column. The point of this slide is that GIL is useful for you even if you never use generic code, because GIL defines a standard terminology. Y iterator is of course a pixel iterator that moves vertically. In this example, we cannot use a row pointer. GIL uses a step iterator. It consists of a pointer plus a step for a total of 8 bytes. The indexing operator multiplies the index by the step. The Y gradient code we just wrote is an order of magnitude slower than the X gradient, but not because of GIL, but because of the accessing pattern. We've been missing the cache all the time by iterating vertically. The code will run much faster if the innermost loop is horizontal. The way to do that is to remember the beginning of the 3 rows and offset from them. The code is very similar, so we won't spend much time with it. The only thing I'd like to highlight is that we can replace the indexing operator with increments and dereferences, just like we can do it for row pointers. Keeping multiple iterators may be inefficient. GIL supports two-dimensional equivalents of iterators, which we call locators. A locator can be moved both horizontally and vertically. Also, it allows for accessing its neighbors in 2D. For example, instead of the 2 iterators in the source image, we could use a single locator and request its upper and lower neighbor. This is the code to do that. First, we initialize a locator at the beginning of the second row of the source image. The locator is a very lightweight object. In this case, all we need is a pointer and a step to go vertically for a total of 8 bytes. The image view allows us to get a locator at any point. The outer loop is the same, and this is how we use the locator. We can use its parenthesis operator to access the neighboring pixels. 1, 0 means access the pixel below the current location. We then increment the iterator and the locator. Notice how the locator allows us to get an X iterator or a Y iterator from it. We can then use these iterators to move the locator. In this case, we move to the next pixel. The operation amounts to a pointer increment. We can also move the locator in 2D. In this case, we do a carriage return. One problem with this code is that accessing the neighbors given their X and Y offsets may be suboptimal, as it involves multiplication and addition. Notice though that the distance between a pixel and its vertical neighbor is constant regardless of the pixel location. GIL allows us to cache that offset by computing it once and then using the cached offset, which amounts to a row pointer offset. In this case, above and below are integer offsets, and accessing them amounts to a row C pointer offset. So far we have seen how to write a horizontal and a vertical gradient efficiently, but it still works only for 8-bit grayscale images. Let us now try to make our algorithm generic. The first thing to change is to replace the concrete image views with templated parameters. GIL operates on concepts. It does not require you to use a specific class to represent your image view or any other GIL construct. It only requires that the object you pass in satisfies the requirements of an image view. One of the biggest drawbacks of generic programming in C++ is that the compile errors can be very difficult to understand. And the reason for this is that you may incorrectly instantiate the algorithm with something that is not quite an image view, but the error you get is not close to the instantiation code, but somewhere deep in the nested code that is unfamiliar to you. The next version of the language will have native support for concepts, but the best we can do for now is use explicit concept checks. This is how GIL does that. It uses the Boost concept check library to enforce the syntactic requirements of the concept. This code has zero runtime performance overhead. However, it can have sometimes significant compile time overhead. This is why GIL wraps the concept check into a function which by default is empty unless a given flag is defined. This statement ensures that the input is a valid model of GIL's image view concept. If you pass something else, you will get an error at this line, which is much easier to resolve. This statement ensures that the destination is also an image view and that it is mutable. And this statement ensures that the two image views have compatible color spaces. That means that they must have the same set and interpretation of channels, although the ordering of the channels is unimportant. And here is the generic version of X gradient. The only significant difference is that we need to loop over the channels of each pixel and compute the gradient for each channel, because the image view now may have multiple channels. GIL has channel-level algorithms that allow us to abstract away explicit loops, similar to the way STL algorithms abstract explicit loops. In this case, we can use transform channels, which is the equivalent of STD transform. It sets each channel of the destination pixel to the result of applying a binary function over the channels of the source pixels. In this case, the binary function computes the half difference of its arguments. We're using a boost lambda expression. GIL provides a number of channel-level algorithms that have STL equivalents. However, GIL's channel-level algorithms are implemented using compile-time recursion, which avoids the explicit loops. Another advantage is that GIL algorithms pair the channels semantically. For example, if the source is RGB and the destination is BGR, the red source channel will correctly be paired with the red destination. So let us examine how generic the code is. Here is some code that uses X-gradient. It is similar to the interface wrapper code that we wrote at the beginning of the presentation, except that its source is an 8-bit RGB and its destination is 16-bit BGR. Here is another example going from 8-bit planar LAB into 32-bit LAB. As you can see, our algorithm works with any color space, any channel depth, any ordering of the channels, and both the source and the destination can be planar or interleaved. Hopefully I convinced you that the code is generic, but how does this genericity affect performance? In this experiment, we will take the most complex scenario where both the source and the destination are planar images, let's say 8-bit RGB. And we will also take the most generic version using the function objects and the lambda expression. Here is the inner loop of what I call the generic enthusiasts version. Let me walk you through this code to show you how complex it is. First of all, the iterator to a planar image can no longer be a simple pointer because the three channels are in different memory locations. Instead, we have a bundle of 3 pointers to the 3 channels. Dereferencing a pixel iterator is supposed to return a reference to a pixel, but again, the pixel is distributed in memory, so instead we return by value a reference proxy class. It's a class that pretends to be a pixel reference, but instead contains 3 references to the 3 channels inside of it. Transform channels uses compile-time recursion and invokes the function object for each set of channels paired semantically. And in order to pair the channels semantically, it uses fully specialized channel accessor classes. And this boost lambda anonymous function object is just pure magic. I hope I have convinced you that this is a pretty complex expression. Let's compare it to the good old C version that does the same thing. I don't even need to explain what it does here. Using Visual Studio 8, here is the code of the good old C version, and on the right is the generated assembly for the generic enthusiasts version. There are 2 sets of differences. First, some code shifted around a bit. Remember, this whole thing is one big loop. There are no branches inside. And the second set of differences is that the generic code has one extra move instruction, which on a modern hardware is typically done in parallel anyway. And to compensate for this, the C version appears to have failed to put a counter into a register. All in all, I measured the performance and I was unable to detect any difference. Okay, by now hopefully you're convinced that the code is generic and that it is fast. The next question is, how readable is the code? It's pretty hard to argue in favor of the generic version, but let me say 2 things. First of all, you don't have to be overly generic. You can actually write an explicit loop. As it turns out, any modern compiler will unroll the loop anyway, and what you get back is the same assembly code. And second, it is not really fair to compare against this non-generic version. What we really should be comparing against are all the different versions that you will end up having to deal with. So from a point of view of code size, debugging, testing, extending, maintaining, we have a pretty clear winner here. So far, I have shown you how to use GIL to write algorithms that are generic, efficient, and readable. The algorithms have been explicit or procedural in nature. GIL also allows for writing algorithms implicitly in a way similar to functional programming. Combining explicit and implicit algorithms can be very powerful, as we'll see later. Implicit algorithms are image view transformations, or changing the coordinate system or other properties of image views. Let me show you what I mean with the following example. Notice that instead of writing the vertical gradient explicitly, what if we rotated the images and reused our code for horizontal gradient? Here is how to do that in GIL. Rotated 90 degrees view is an example of an image view transformation function. It takes an image view and returns a 90-degree clockwise view of it. It's very fast and shallow, like all other image view transformation functions. It doesn't do any rotation and it doesn't copy the pixels. It simply returns a view whose x iterator is the y iterator of the source view. Of course, this way of writing y gradient will be very inefficient, but not because of GIL, but because of the cache-friendly memory access pattern, as we discussed earlier. Here is how to compute the gradient over the blue channel of an RGB image. Nth channel view is a view transformation function that takes a source view and an index and returns a single channel view of the nth channel of the source. In this example, it returns a view whose x iterator has a step of 3. But if you give it a planar image instead, nth channel view is smart enough to return a view whose horizontal iterator is a simple raw pointer. Again, GIL picks the simplest, most lightweight construct that can do the job. Here is another hypothetical example. What if you wanted to compute the gradient just over the even pixels of the image? Subsampled view takes a source view and returns a view that steps over x and over y by the specified steps. You can also pipe those views together. GIL can often optimize complex view transformations. For example, if you create a subsampled view of another subsampled view, the result is a single subsampled view whose step is the product of the two input steps. Here is another example. Very often we want to compute the gradient of the luminosity of the image. In this example, color converted view takes an arbitrary view and returns a view that is 8-bit grayscale. Just like other view transformation functions, it doesn't do any color conversion. It simply puts 8-bit grayscale glasses on and lets you look through them at the view. GIL has a number of view transformation functions that do all kinds of transformations. They are described in the tutorial and in the user guide. Here is an example of using image view transformation functions. First, we read an image, we crop it, we color convert it, we rotate it, we subsample it, and then we can call the X gradient algorithm we just wrote on it, and it will do the right thing. Notice also that all of these image view transformations are instant and shallow. No pixels are ever copied. Everything is done on the original data. All the work is done inside the X gradient algorithm. Of course, if you're concerned that piping all of these image views can slow the algorithm, you can always copy the result into a temporary buffer before running the algorithm, as we will see shortly. Now let us talk about treating images as one-dimensional arrays of pixels. Notice that our X-gradient algorithm has an unusual axis pattern because it doesn't apply to every pixel in the image. In particular, it skips the first and the last column. One idea is to write a version of the algorithm that applies to every pixel, but invoke it on a subimage views that exclude the first and the last column. Here is the code to do that. Subimage view is an image view transformation function. It takes a view and it returns a view of a rectangular subimage of the source view. The subimage is specified with the top left point and the dimensions. X-gradient unsafe is the version of X-gradient that applies to every pixel. We call it unsafe because it accesses pixels outside of its allowed views. It is an example of what we call a canonical algorithm, an algorithm that applies the same operation at each pixel of the image. GIL has some special mechanisms to help write canonical algorithms. Here is one way to do it. Notice that GIL can give you a one-dimensional random access iterator that traverses all pixels left to right and top to bottom. You can use familiar STL-like interface using begin and end. You can also loop through the pixels with an index. GIL provides std vector-like interface that gives you the 1D size of the image. We also have a bracket operator to return the pixel corresponding to a given index. Using 1D iterators is simpler, but it is slightly suboptimal, as discussed in the design guide. We can also abstract away explicit loops into pixel-level algorithms, similar to the way STL abstracts loops into algorithms. Transform pixel positions is similar to std transform. GIL provides a number of pixel-level algorithms that apply to all pixels of an image view. Instead of ranges, they take image views. Many of them have equivalents in STL or ASL. Transform pixels, for example, is similar to std transform as it passes pixel references to the function object. For our example, however, a source pixel reference is not sufficient as we need to access its neighbors. This is why we use transform pixel positions, which uses locators instead. Some GIL algorithms have performance overloads. For example, copy pixels between two interleaved images may resolve into a call to memmove. Fill pixels may resolve to a memset where appropriate. We will conclude our tour of GIL core with a discussion of GIL's metafunctions mechanism. Let us start with a motivating example. Consider this non-generic code that computes the gradient of the luminosity of a 32-bit RGB image. Color converted view performs color conversion every time a pixel is accessed. In our algorithm, we end up accessing each source pixel twice on average. Sometimes it may be more efficient to store the color converted pixels into a temporary buffer and run the algorithm on the buffer. Here is how to do that. First, we create a new 8-bit grayscale image container, with the same size as the source. What this does is it actually allocates the memory for the pixels. We then copy the color converted view of the source into the image. View of image returns a mutable identity view of the corresponding pixels of the image. Finally, we run the gradient algorithm over a constant view of the temporary image. We can simplify the code a bit using copy and convert pixels, which does exactly that. Now the question is, how do we make this code generic? Here is how to do that. The body is almost the same, except that we need a generic type for the temporary image. We need the temporary image to be one-dimensional, or in other words grayscale, but its channel type to be the same as that of the source view. Image type is an example of a GIL meta function. GIL provides meta functions to construct images and image views from components, such as given color spaces, channel types, and memory layouts. It also allows for constructing an image or a view that is just like a given image or view, except that some of its properties may be different. We specify the properties that differ and put use default for the ones that don't. GIL also has type analysis meta functions of the form GIL construct is property, as shown in this example. That concludes the mini tutorial of GIL core. Let us now talk about the GIL extensions mechanism. GIL extensions are modules built on top of GIL that address image-related problems that are usually open-ended and not directly related to GIL's main objective of abstracting image representations from image algorithms. We have currently open-sourced 2 GIL extensions. One provides support for runtime instantiated images and image views, and the other provides support for image I/O. Let us now talk about the runtime image extension, or dynamic image extension. As you have seen, many of the image parameters are part of the image type, which is very important if we want to achieve efficient code. However, in practice this can be a problem since image parameters may not be available at compile time. For example, what if you want to read an image from disk? In this case, we use any image and any image view which are provided in GIL's dynamic image extension. First, let me show you how to create and use dynamic images. Then we will see how to change our algorithm so it works with dynamic images. The first step in creating dynamic image view is to specify the set of image views it is allowed to take. In this case, our view can be 8-bit or 16-bit and can be grayscale or RGB. User-defined views can also be used here. Then we instantiate the runtime view with a list of possible views. The default constructor automatically default constructs the first view type, similar to Boost variant. We can then change the image view at runtime. Enumerating explicitly all possible types can be cumbersome. GIL allows you to enumerate types implicitly by specifying dimensions of variation and computing their cross product. In the above example, we define the set of all 8 or 16-bit RGB or CMYK views that are planar or interleaved and that have step or non-step property. That defines 16 possible view types. False means mutable image view. You can also concatenate, in other words union, type enumerations, both implicit or explicit, or other unions. In this example, we added another 2 views to our list of 16. Now we can use that extended list to create our runtime view just like we did before. GL algorithms and view transformation functions can also take runtime images and image views. They are also efficient because the dynamic branching happens at high level, in other words, once per algorithm instead of once per pixel. Now, let us see what we need to do to make our X luminosity gradient algorithm take a dynamic image. For simplicity, let us assume that only the source is a runtime view, although GL allows you to use algorithms in which multiple arguments are runtime specified. The first step is to wrap the algorithm into a function object whose application operator takes exactly one parameter, namely the source image view. The other parameters, in this case the destination image, are stored as instance variables in the function object. Notice also that the function object must have a result type def. The second step is creating a function overload of our algorithm that takes any image view. Any image view is the runtime specified view. It contains inside an index identifying the current type and a memory block large enough to store the instantiated view. The design is similar to that of Boost variant, but GL is currently not using Boost variant. As you have seen, the dynamic view is templated over the set of allowed views. GL's apply operation goes through a switch statement, casts to the correct image view, and invokes the function object with the result. When using runtime constructs, you are implicitly operating on a collection of types. Instead of transforming a single type, the entire collection is transformed. For example, suppose you have any image that could be 8-bit RGB or 16-bit planar CMYK. When you request the view associated with a runtime image, what you get back is a runtime view, which can be respectively 8-bit RGB or 16-bit planar CMYK. If instead you request the constant view of a runtime image, you get back any image view of the corresponding immutable view types. If you now call nth channel view of the immutable views, you get back the collection of immutable step views. As I mentioned before, most GL algorithms can take runtime views in all places they take templated views. For example, copy pixels can copy freely between templated and runtime views. If the two templated views are not compatible, we get a compile time error. If we invoke copy pixels with incompatible views specified at runtime, we get an exception. Since most algorithms and view transformations already take runtime views, that allows for writing high-level algorithms in which the runtime aspect is abstracted out. For example, this code can read an image from disk and write it back transposed. You can instantiate it with a templated image, but you can also instantiate it with a runtime image, in which case it will transpose the image while preserving its native color space and channel depth. In this example, the runtimeness of the image is abstracted out. There are clear benefits and drawbacks of using runtime images. It is certainly very powerful to specify any aspect of the image at runtime to treat different image types in a uniform way or store them in the same container, for example. When used properly, they have no practical performance implications. On the other hand, using dynamic constructs requires writing some glue code, as we saw. Although GAO doesn't prevent you from creating runtime objects that operate on lower levels, such as any pixel iterator or any pixel, such use is discouraged due to the performance impact of having the dynamic branch executed at each pixel. Also, dynamic images may significantly impact the compile time and the executable size, as they instantiate the algorithms for every possible set of parameters. However, GAO has a special mechanism that can identify and eliminate template instantiations that are at assembly level identical. This work is a result of collaboration between Professor Jaco Jarvi from Texas A&M University and myself. GAO also has an I/O extension that currently supports reading and writing some commonly used JPEG, TIFF, and PNG files. Using I/O requires linking against the corresponding file format libraries as described in the documentation. You can read an image from disk. GAO allocates an image of the appropriate size and reads its pixels. There are three ways of reading images. If you know the type of the image on disk, you can read it into a templated image. If you are wrong, you will get an I/O exception. Often you don't care what the format is on disk, but you just want your image converted to a given format. You can use the read and convert method to read an image and convert it on the fly without any extra memory. Finally, you may want to read an image on disk in its native color space and channel depth. You can do that by reading into a runtime specified image. GAO will check the allowable types of your any image and instantiate the first one that is compatible with the destination. If none are compatible, it will throw an exception. You can also read an image directly into a mutable view using the same three methods. The difference is that image views don't manage memory. This could be very powerful. For example, you could read an image upside down or read directly into a sub-image of an existing image without using any extra memory. However, since image view dimensions are fixed, the file on disk must match the same dimensions or an exception will be thrown. We can also use write view to write runtime or templated image views to a disk. Now let us conclude our presentation with some thoughts on where we are going with GAO and why you should consider using it. Here are the top 10 reasons people might not use GAO. I'm going to say a few words about each of them. The first one is about hand-tuning generic code. Although I showed you how GAO can produce the same assembly as a good old C code, if you want to make this code faster, you can do much better than the C version. You can unroll the loops, use prefetching, use SEC optimizations or assembly subroutines, something clearly you can't do in the generic version. Let me show you how GAO's approach to be both generic and down to the metal efficient. We will use an example of GAO's copy pixels algorithm. On the bottom, we have a subset of all the different concrete versions of copying between different formats that people will end up having to write today. And on the top, we have a generic version. The generic version simply loops through and copies every pixel. If things are done right, the generic version will do the job of any of the concrete versions. The problem is that the concrete versions can be implemented much more efficiently. For example, if we know that we're copying between two planar RGB images, we can just do 3 mem moves, one for each color plane. This is about 10 times faster than the generic version, and there is clearly nothing that we can do in the generic version. to that effect. GL's approach is to provide overloads at the appropriate levels of genericity. It provides an overload of copy pixels triggered when both images are planar. It simply does a mem move for each plane. Similarly, if both images are interleaved, we can do a single mem move. The generic version is only used as a fallback scenario. For example, if you use a synthetic image view, there is no way to do any of these optimizations. The advantage of this design is that all the performance-optimized overloads are still generic. In other words, they apply to an entire open class of problems. For example, someone may introduce a new 5-channel color space. When they copy between two 5-channel planar images, GL will issue 5 mem moves. No extra code needs to be written or changed for the new image types to be efficient. If you already have adopted another library that solves the problem of abstracting images from imaging algorithms and it does the job for you, then stick with it. However, I can guarantee you that no one library will be optimal in all cases. The advantage of GL is that it is very unintrusive. All you need is to include the GL header files and you are in business. That means that even if you standardize on another library, you can still just take one method and use GL for it. If you already have imaging code and you have invested lots of time in it and it's working, then by all means use it. GL is unintrusive and can be freely mixed with non-GL code. Even better, if your algorithm is valuable, consider gilifying it and sharing it with the rest of us. GL does not impose any extra library dependencies. All of GL is in header files. You only need to add extra libraries if you use GL's I/O module. GL is part of Adobe's open source libraries. We have a team of people dedicated to supporting Adobe's open source libraries. We have newsgroups, mailing lists, wiki pages, and all the tools you need. You can also try emailing me and my colleague Heilingen directly. We're always happy to hear from people how people use GL. GL should compile on any modern C++ compiler. We have compiled it on Visual Studio 7 and 8, GCC 3.2 and 4, and on both Windows and Mac. I even have a version of GL running on my Pocket PC to do face detection. I had to tweak a couple of boost files to get boost to compile on the Pocket PC. Compile errors in generic code can be a nightmare. This is not a fault of GL, nor is a fault of generic programming. C++ will catch up in the next release, which appears to be very exciting. GL uses the concept check mechanism to alleviate this problem. GL has a steep learning curve, but if you follow this presentation, you already know most of GL. If you know STL, GL is very easy to learn, as everything from concepts to name conventions is similar. If you don't know STL, then learn STL. It's a really good thing for your career. Although generic code can result in code bloat, GL has a special mechanism you can enable to identify and reuse assembly-level identical code. It is disabled by default because it can slow down compile time. We have measured up to 70% code reduction in some cases. Some compilers already have options to optimize out assembly identical routines. GL's active code bloat reduction mechanism can be used with the compiler options to further reduce the code, sometimes up to an additional 30%. Finally, one common critique of generic code is that you cannot easily tell what it does, so you can't know if it's efficient. I don't have a good solution here. My advice is write your algorithms, run them and profile them. Then if you are not satisfied with the performance, you will have to look at the bottlenecks and understand exactly how the library handles them. It is true that generic code is more opaque and makes you feel less in control, but the same argument applied earlier when high-level languages like C were introduced. The assembly guys were complaining that you can't possibly trust the compiler to do an optimal job, and you can't really tell what exactly it will do. And yes, the compiler-generated assembly is often suboptimal, but everybody today uses high-level languages. Similarly, the power that you get with generic code clearly outweighs its disadvantages. GIO is used in several ongoing projects at Adobe, including features for the next generation of Photoshop. We're also exploring potential collaboration with universities such as the Open Systems Lab at Indiana University. We're also exploring the possibility of proposing GIO to the Boost libraries. In conclusion, I showed you how GIO abstracts away the image representation and allows you to write the algorithm once and have it work for images of any type. I showed you how GIO algorithms provide overloads and can achieve down-to-the-metal performance. The dynamic image extension allows you to specify any image parameter at runtime without a performance penalty. GIO operates on concepts. That means that you can replace just about any part of GIO, its pixels, iterators, locators, image views and algorithms, with your own, and the rest of GIO will work as expected. It means that one developer can provide, say, 64-bit channel type, another can provide XYZ color space, a third one can provide a fully synthetic image view like the Mandelbrot set, and we can use the X gradient code we just wrote to compute the gradient of the Mandelbrot set at 64-bit depth and represent it in XYZ color space. Furthermore, all these engineers don't need to coordinate with each other or even know about each other, and the GIO core does not need to change. The biggest reason I believe GIO will be successful is that it is completely unintrusive. It doesn't force you to link against specific libraries. It doesn't require you to use specific classes or even subclass from specific classes. It doesn't require your data to be in a specific form. It works natively and efficiently with what you've got, the way you have it and the way you want it. I would like to acknowledge the following people for their contribution to GIO. Specifically, I would like to single out Alex Stepanov. His programming class at Adobe has directly inspired this project. The reason GIO resembles STL is that we were directly influenced by the creator of the STL. You can get all the GIO source code and documentation on GIO's website at opensource.adobe.com/GIO. Finally, GIO is a two-way street. We would like you to use GIO, but we also very much encourage you to join us in sharing your ideas and your code with the rest of us. Thank you for listening.